Okay, so now we're going to talk about velocity. And when we're doing a velocity analysis, we have two ways that we'll handle this in this class. So one is MATLAB, which you might have expected. The other one is going to be using a graphical method. And when we talk about velocity, we have kind of where are we located. So if for position, we had our vector was position, which had where we were located in terms of the distance and the angle at which that distance was. And if it was scalar, it was just distance. Velocity will be similar, where if we want it as a scalar, it'll be speed. So that's the change in distance as distance over time. And velocity will be our position over time, where we want to consider not just our speed, but also the direction in which speed happens. So velocity is the time derivative of position, and as a result, it's going to be a vector. It has a location, it has a angle and a magnitude, and it'll behave differently based off of what type of scenario we're at, what type of motion we have. So at the beginning of the semester, we talked about how we could deal with pure rotation. We could have pure translation, or we could have a complex motion, which would be a combination of both. So let's talk about some of those different types of motion and see how we can handle them. So for pure translation, that's our easiest scenario. We have 2 points, A and B. All of our velocities on any 2 points on a rigid body will be the same. So when we say the velocities are equal, that means that not only do they have the same magnitude, they're pointed in the exact same dimension. Next, we'll have rotation. So pure rotation, the book says that we have something rotating around a point on the body, and they say as if we're rotating about point A, we can actually rotate about any fixed point in a pure rotation scenario. So if we have RB, and so we're going to say that all points rotate about an unmoving center. And the center could be on the body, it could be off the body. But if we want to calculate our velocity, we could say that the velocity of point B, A is going to be constant, so that's the length that B is away from capital A. And that vector is A times our unit vector E, so A times cosine theta sine theta. And if we take the derivative of that, A doesn't change. So we're just taking the derivative of our unit vector E. Now, a few classes ago, we did this. Does anyone remember? We're going to pretend that you are all here in person. You're not, but, maybe you like listening to these videos like Dora the Explorer and give me a shout out. But if we take the derivative of E, that gives us omega times our unit normal. So we have A times that derivative of E, so A omega, our unit normal vector, or A omega negative sine theta cosine theta. So the magnitude of our velocity of point B is A times our angular velocity omega, and our velocity of B is perpendicular to that radius r, that position vector of B. So, good things to remember, and now we can describe complex motion. So complex motion, we already defined that it's going to be the combination of two, but let's use some calculus to help us through that, because who doesn't like doing calculus for fun? So we have point A and point B. Point B, A is, we're going to refer to everything such as that. So really we have some object that is both translating and rotating, but when you want to describe what's going on, it's good to choose a fixed point. So we're going to have the velocity of B is equal to the velocity of A plus the velocity of B relative to A, because that's going to allow us to say that A is translating and B is rotating around A, even though we might say that B and A are both rotating around another point. It just makes things a lot easier for us. So we can say that A is translation, B over A is rotation, and then say that the velocity of B is going to be equal to the velocity of A plus A omega times the velocity of N. And let's pause this because it's going a little bit faster. Didn't put an auto pause in there. So the book start skipping to just scalars real fast because it means that we have to be less picky. I'm going to stick with vectors for a little bit longer and then join the book in just going back to scalars and considering the magnitudes of velocity. But a omega n, we can think of n is going to be in that direction away. Omega in this case is counterclockwise, which is positive. Makes sense because if theta increases, that would be a positive angular velocity, and that is going in the counterclockwise direction. So if we want to calculate this using vectors and our cross product, we can say that our rotational velocity is going to be omega cross our position. And that's going to be that RB with respect to A. So omega is in the positive K direction. So nice thing about that, you can give a nice thumbs up if you're playing along at home. Then we put our pointer finger in the same direction as, you could do it with the diagonal that I have on there, or you could just say it's going straight up, and then your middle finger will go towards the left. So that would be the direction we'd expect to see rotation, so it's going to be omega cross RA. So that's how we can calculate these things, and it's going to be one of the ways that we talk through a lot of these problems. So the last scenario before we get into linkages would be a velocity of a point that's moving on a rotating link. And so this is nice and fun because not only do we have rotation, but we also have translation along the link. So that means that if we describe the position of A to B, we have that the position is RB is equal to A times our unit vector E, and neither the unit vector nor the length A are constant. So A is not constant, the unit vector direction is not constant, they're both moving. Another thing we can do if we want, we can double check the system, check the degrees of freedom. So here we'd have 3 links for the ground, the rotating link, and the sliding point. And we have a 1 pin joint, 1 full slider joint. So we have 2 degrees. Yep, there we go. We have 4, so 3 times 2 is 6 minus 4. 6 minus 4 is equal to 2. So 2 degrees of freedom. That's less surprising. And as we go through, we can take the derivative, and we would need the product rule to take this derivative. So that would give us the derivative of A with respect to dt times our unit vector, and then we have that added to A, take that as a constant, times the derivative of our unit vector. Another way to write that would be that if we want to know the velocity of B, we would need to know the velocity of A along that translation, how much it's sliding, as well as our angular velocity omega. So that matches with the 2 degrees of freedom that we would expect to need to know. Another way you could see those 2 degrees of freedom would be the angle theta and the distance A for our system. Okay, so now we're ready to start taking things a little bit more abstract. I will set that to another video.